Up to now, all of the area measurements that we've done have been using a map. So we're in one form or another tracing or counting the area contained within a drawn boundary. And what we would like to be able to do is to be able to work directly from coordinates. Every time we take data, plot it on a map, whether it's on paper or otherwise, and then measure it over again to calculate something else like area, we're giving ourselves several more opportunities for errors, either systematic error and blunders or random error that is going to be associated with any kind of measurement, no matter how careful you are. So in chapter 12, Galani goes through a method for calculating area directly from coordinates, which is pretty inscrutable the way he describes it. So I thought I would cover the same thing, but try to make it a little bit clearer what's going on here. And one of the things that I want to emphasize is that this is it's generally applicable to any closed polygon that you have coordinates for. And you don't have to do the graphical business, which is shown in this demonstration example. But the pictures are shown simply so that you can see how the method works. In practice, you don't have to do any of this. You just write down the coordinates and you do the calculations that are described by what's called the shoelace equation, for reasons that we'll get to in a little bit. So anyway, let's get started with this. Here's a polygon, A, B, C, D, E, and let's suppose that we have the coordinates, east and north, x and y, for all 5 points. This actually is the outline that Galani uses in his example. Here is his figure showing the outline, which didn't really draw attention to the outline itself very clearly in this picture. The construction, the E prime, D prime, B prime, and so forth, are all to show you the coordinates of the points involved. Each point, A, B, C, D, E, has an X and a Y coordinate. And it's not very clearly drawn, but you can see that each point does. The key to this method is to break down the figure, the closed polygon, into a series of trapezoids whose areas you can easily measure. And you do this by breaking down the area into a set of trapezoids that you sum, and then another set of trapezoids that you subtract. For example, we take our figure here, A, B, C, D, E, and I've created 2 trapezoids, area 1 and area 2, outlined in blue. They are both 4-sided. Now these have parallel sides. You can see that the trapezoid number 1 up at the top has 2 horizontal lines at D prime to D, and then above that at E prime to E, but they're different lengths. The D prime to D is longer than E prime to E, but we have this 4-sided figure. Same thing with trapezoid number 2, which is described by the line at the bottom, C prime to C, and the line at the top, D prime to D. And both of these areas can be calculated quite simply by multiplying the height, that's the y coordinate at the top minus the y coordinate at the bottom, times the average value of the width. In other words, here's a generic trapezoid with the upper value, y2, and the lower value, y1, gives us a delta y, and then the average height, which would be x1 plus x2 divided by 2, gives us the width, and the area of this trapezoid is simply y2 minus y1 times x2 plus x1 all divided by 2, or twice the area is equal to y2 minus y1 times x2 plus x1. So now let's apply that to these two triangles here. And of course, that gives us more than the area of the figure ABCDE. And so what we have to do is create a few more trapezoids and subtract those, which we do in this way here. Now we've got 3 more trapezoids, number 3, number 4, and number 5. Now 4 and 5 are triangles rather than 4-sided figures, but that's perfectly all right. We could still do the same thing. We've got a height, the upper value of y minus the lower, times the average of the two x values, which in this case is just going to be half of the single non-zero x value. So looking at triangle 4, for example, here is the upper value of y, here's the lower value of y, and this time the upper value for x is 0 and the lower value is out here at b, and so the height, or the width rather, is going to be 1/2 of those values. And so that product there will actually give us the area of triangle 4. The area equals 1/2 base times height. So now, if we calculate the areas 1 and 2 and then subtract off 3, 4, and 5, we will have the area of the original polygon ABCDE, like so. Now we just have to do the calculations. And those looks like this. I've drawn the positive areas, the ones that we add together. Those are areas 1 and 2 in blue, and the negative areas, the ones that we subtract, in red. And each one of these is done in the same form. The upper value of y minus the lower value of y times the sum of the upper and lower values of x. Now these are each giving twice the area, so when we sum these up, adding the blue ones and subtracting the red ones, then we divide everything by 2, and that gives us the final area. Now multiplying this out leads to some simplifications, and what I've done here is I've expanded the products on each of the 5 calculations, and when we add all these up, we get a number of cancellations, and the final result is this expression here. And here's the easy way to remember the form of this equation, called the shoelace equation. You can see the resemblance to laced shoes. If you look at the first term here, XAYB minus XBYA, that's the first term. And if you just follow this list, adding the products of the terms that are linked by the black arrow and subtracting the products that are linked by the red arrow right down to the bottom. And notice that we go here through A, B, C, D, E, and then A again at the bottom. That series of calculations will give you double the area. So just do all those multiplications and sum them up and then divide by 2, and you'll have the final area.